So today I have the pleasure to introduce an outstanding differential geometry, Professor Wolfgang Ziller from Pennsylvania. Well, he will be talking about geometry and topology, cohomogeneity, one manifolds. Let me just point out that Wolfgang came to Brazil last year for the first time, and this year he's back. I heard that he already accepted an invitation for next year, so that's very good, right?
Well, first, I'd like to thank the organizers and IMPA for the invitation. It's a pleasure to talk here, and I think I'm starting to fall in love with IMPA and Rio, or maybe with Rio and IMPA. I'm not quite sure in which order. It's certainly a pleasure to be here again. What I will talk today about is on a certain class of manifolds that I've been thinking about off and on for the last 10 years. And I've started falling in love with these manifolds. I keep discovering new properties and lots of new problems that haven't been solved yet. And what I'd like to do today is convey to you my love for this subject, and maybe also to get some of you interested in thinking about some of the problems I will mention. First, I should explain what a cohomogeneity manifold is, of course. So the origin in this idea is something that all of us geometers have done when we first learned geometry. We studied surface evolution in 3 space and used them to construct various examples. Sometimes they're easy to construct, sometimes hard. And certainly surface evolution is a great source for geometric intuition. These manifolds that I'll talk about are higher dimension generation of the surface evolution. In fact, if the name hadn't been given already, I would have preferred something like rotationally symmetric manifolds to convey this a little bit better. But they have already been named cohomogeneity manifolds by Xiang a long time ago. So here's a definition. An n-dimensional manifold, I also assume it has a metric on it and is complete. It's called a cohomogeneity manifold if a Lie group G acts on this manifold by isometries, and the quotient of the manifold by the Lie group is one-dimensional. So this is slightly larger than the set of homogeneous spaces, which also have been used in geometry a lot to construct examples. But this class of manifolds is more difficult to deal with, both as far as constructing examples is concerned, and also as far as the topology of the space is concerned. Because right now, the Riemannian metric is only a background metric. It doesn't play a role yet. Later on, when I talk about the geometry of these spaces, then we will assume the action G by isometries. Right now, it's just a background metric. So here are the first kind of simple examples. Surface in 3 space. So surface evolution, and they come into various categories as far as the action of the group is concerned. The group here is always a circle. So first, there's, for example, a sphere or a compact surface evolution, which has 2 fixed points, the north and south pole, and all the other orbits are circles. And then another example is where the action has no fixed points, like on a torus, where all the orbits are simply circles. And then another example would be R2, on which a circle acts with a single fixed point, like a paraboloid of revolution. And then finally, there is something like a cylinder in 3 space, on which the circle also acts with only circle orbits, but the manifold is not compact. So these are the 4 types that appear in 3 space, and we will generalize these in various ways. In particular, I will not necessarily view them as submanifolds of Euclidean space. In that case, even here I have a few other examples, like the Klein bundle on which a circle acts, or the Möbius band on which a circle acts, which will also appear in this category. But these examples, or their higher dimensional generalizations, of course, I can also do this in Rn+1 with a hypersurface of evolution. These are very simple examples, and I want to consider something of a more interesting nature, or more complicated nature. Here is the first example that's a little bit more complicated, and that indicates some of the things that can happen, namely the well-known action of a 2 torus on the 3 sphere, which I can view right down as follows. I regard the 2 torus as a pair of complex numbers, unit complex numbers, and S3 as a pair of complex numbers which lie on the 3 sphere of radius 1. And I just let the 2 torus act by multiplying each coordinate with A and B. And of course, now the orbits are, there are 2 special orbits. In one coordinate, I have a circle which I depict like this. In the other coordinate, I have another circle which I depict like this. They're actually linked like this in 3 space. That's the ordinary picture of a 3-sphere. And the other orbits are simply 2 tori, which are simply tubes around this circle of a varying radius, and they happen to agree with each other. So this is a union of S3 as 2 circles and 2 tori as distant spheres around these circles. Particularly, they are not fixed points anymore, but the orbits are either 2 tori or circles. So the 2 torus orbits are called principal orbits, and the circle orbits are called singular orbits. A more complicated example, and in fact, this is one of my favorite examples that depicts a lot of the intricate behavior of these manifolds already, is a well-known action of SO3 on the 4 sphere. But not in the standard way that we did over there. Of course, on S4, I also have an action of rotation by SO4 fixed to north and south pole. That's as simple as the action over there. But here, the group is smaller, and it's a group by SO3 acting on the 4 sphere. Which I describe as follows. Consider the 5-dimensional vector space of 3 by 3 real symmetric matrices with trace 0, and which are symmetric. So that means I have 3 off the diagonal, 2 on the diagonal. That's a 5-dimensional vector space, on which I have an inner product, just a trace of the product of the matrices. So it becomes a Euclidean vector space. On this Euclidean vector space, I simply let SO3 act by conjugation of the symmetric matrices. So GA, G inverse. And of course, the action preserves the inner product, and therefore it also acts on the 4 sphere sitting inside this vector space, inside the 5-dimensional vector space. And I claim this action of SO3 on S4 is cohomogeneity 1. And this one simply sees by observing that certainly every symmetric matrix is conjugate to a diagonal symmetric matrix, which I denote like this, with the eigenvalues on the diagonal. The trace is 0, summation lambda I is 0, and this means that the matrix lies on the 4 sphere. So this is a great circle inside this 5-dimensional vector space. So therefore, this is 1-dimensional. Every orbit meets this 1-dimensional circle, and the quotient must be 1-dimensional. So it's a cohomogeneity 1 action. Let's look at the orbits and see what the structure of this action looks like. Well, I just take orbits of symmetric matrices. So one case, the principal orbits will be when all the eigenvalues are distinct. I can assume they're increasing in size. And then what's the orbit? Well, take the orbit of these matrices. That's SO3 divided by the group that fixes these matrices. And that group is simply S of O1, O1, O1. That is, I can conjugate with plus or minus 1 over the diagonal. And that preserves these kind of matrices. That's the isotropic group of this kind of matrix here. Of course, with determinant 1, since it sits inside SO3, so it's really Z2 cross Z2. So the principal orbit is simply a quotient of SO3, which I can also regard, if you want to, as a quotient of the twofold cover, which is S3, by the inverse image of this in S3, which is a quaternion group. So it's a space form. The principal orbit is a space form. And what are the other orbits? The singular orbits, I call them B plus and B minus. They consist of those matrices, orbits of those matrices A, where 2 eigenvalues are the same. And there are 2 cases, either they're both negative or both positive. These are different orbits. And let's take a typical one in F that belongs to 2 negative eigenvalues right here. This must be this diagonal matrix. Trace 0, 2 eigenvalues the same, summation lambda I squared equal to 1. And of course, then, what's the fixed point group of this matrix? I can rotate in these last 2 coordinates arbitrarily, and here I can multiply plus or minus 1. So the isotropic group is S of O1, O2 diagonally inside SO3 with determinant 1. That's what S means, since it sits inside SO3. That's just SO3 over O2, which is an RP2. So one single orbit is an RP2, and the other one, I take a matrix where I have 2 positive eigenvalues, which are the same. And then, of course, something similar happens. Now I can rate in the first 2 coordinates arbitrarily, plus or minus the last one. So that's S of O2, O1. Conjugate embedding, actually. So therefore, the quotient is the same. It's again RP2. And observe that it's simply the antipodal RP2. That is, if I take a matrix in here, multiply by minus 1, I get one with 2 positive eigenvalues. Therefore, these 2 orbits are antipodal to each other inside the 3 sphere. Notice also that these orbits are what are called the very nice surfaces inside S4. So they're well-known examples of minimal surfaces inside S4. And so the orbit structure of this example is the principal orbits are the space form. The exception of the singular orbits are 2 very nice surfaces antipodal to each other. And notice that the distance of these 2 singular orbits inside S4 is actually very small, because on this great circle, you can compute the distance from here to here is actually just pi over 3. So unlike in the previous example over there, the distance of the two singular orbits of pi over 2, here they're more narrow. So it fills the 3-sphere in a more efficient way. And so this is a more intricate example, and that's typical of what happens in many other examples. So I want to generalize this to other cases by looking at some other examples which are of a somewhat similar nature, which indicates that even in low dimensions, like in dimension, before I go to other example, dimension 4, I'm sorry, let me look at one high dimension example, just so that you won't think these actions only exist on very nice spaces like spheres and tori that I discussed so far. In fact, one part of the subject actually consists of looking at these actions on very nice spaces. So, for example, on spheres that are classified by Xiang and Lawson a long time ago. They're very beautiful actions on spheres. There are very many of them in higher dimensions. Such actions on symmetric spaces also have been considered a lot. In fact, we heard about some of them in this conference already. And they are classified now by Koros. They have beautiful properties. But what I want to consider is manifolds that are more complicated. In fact, eventually I want to construct new manifolds. So the next example illustrates that these things can be more complicated by discussing another old and well-known example, namely an action of the group SO2-SON on what's called the Cavier sphere. This was also discovered by the Xiang, actually by Xiang and Calabi. Calabi suggested the example first, but as usual, Calabi doesn't write anything down. He then told Xiang about it, and Xiang generalized it to higher dimensions and wrote a paper on it. It's a beautiful example. So here, in the first line up there is the definition. It's a Briescon variety. The polynomial depends on a certain integer d. So I raise the first coordinate, contact coordinate to a power d. And then, of course, I intersect with the sphere as usual for a Briescon variety. And then I get a manifold. If you count the dimensions, it has dimension 2n minus 1. But it depends on the choice of the integer d. So it's a family of 2n minus 1 dimensional manifolds. And this has been examined quite a bit by topologists. In particular, one knows that this is an exotic sphere. That is, it's homomorphic to a sphere, not diffeomorphic. If 2n minus 1 is congruent to 1 mod 8, so dimension 8k plus 1, and if the integer d is plus or minus 3 mod 8. Whereas, for example, if d is plus or minus 1 mod 8, it's diffeomorphic to a sphere. So these manifolds both represent the ordinary structure on a sphere and also an exotic structure on a sphere. So it shows that these manifolds actually can have very interesting and complicated topological behavior. The action is very easy to describe, and this is on the next line down there. So the group is supposed to be SO2-SON. I present it by either the I theta in SO2 and by A, the matrix in SON. I act on these n plus 1 complex coordinates. Notice I pair the last n together into a column vector, multiply with the real matrix A. That gives me another column vector which I transpose. And then the first coordinate I multiply with a complex number, but notice that I multiply with different powers. The square of the complex number in the first coordinate z0 and the dth power in the second coordinate. And the reason is I want to preserve this equation that defines the Briescon variety. And you notice if the first one is squared, the second one is raised to the dth power, that still satisfies the equation. The SO2 action preserves this equation, and the SON action, it just rotates the last n coordinates. That clearly also preserves summation some z1 squared of zn squared. This group acts on this manifold, and it's not hard to see, although I won't do this in detail now, that indeed the quotient is one-dimensional. But I want to at least describe the regular orbits and the singular orbits of the action, because they are surprisingly simple. I do it only for d odd. D even is a little bit different, but the exotic spheres occur in d odd anyway, so that's sufficient. The singular orbits are 2, b minus, b plus. For b minus, I take, so G is SO2, SON, remember? The subgroup is now SO2, SON minus 2, but with a strange embedding. And this embedding is very important to understand this example. So here in the next line, define it. Either I theta A, which lies in SO2, SON minus 2, has to be mapped into the group G, which is SO2, SON. I send either the I theta in the first coordinate, and in the last, in SON, I combine the theta, the angle, into a 2x2 rotation by angle d theta. So R of d theta is simply a 2x2 rotation in the first block. And then the matrix A, which is n minus 2, goes into the last block. So it's again a block form. But notice the embedding depends on integer d. Okay. On the other hand, the quotient, it's not hard to see, it's very simple. It's simply the unitangent bundle of a sphere. So it doesn't depend on d, but the structure of the manifold does. The other orbit is b plus. It's g divided by O n minus 1. Here I write down the embedding of the matrix A in n minus 1. I take that A in the first coordinate, SO2. And here I take a block form, that A plus or minus 1 in the first coordinate, and the remaining matrix A in the last coordinates. That's embedding into G. And now, again, it's not hard to see. The manifold is very simple. It's a circle across a sphere divided by Z2. That's all. Then the principal orbit, the regular orbit is written down here, is G mod the group H, which is Z2 cos SON minus 2. Embedding is, again, a little bit more complicated. Epsilon lies in Z2. A lies in SON minus 2. I put epsilon in the first coordinate. And here a block form matrix, epsilon, epsilon in the first diagonal entries. And then the matrix A. That's how H sits at G. And it's not hard to see. I don't think I wrote this down. The quotient G mod H is simply a circle cross a unit tangent bundle of a sphere divided by Z2. So also very simple. So the orbit structure is surprisingly simple. Right? The principal orbit is just a circle cross the tangent bundle of unit tangent of the sphere, essentially. The singular orbits are unit tangent of the sphere and S1 cos Sn minus 1 divided by Z2. Very simple manifolds. How does D enter? D enters in the way that these things are glued together into the big dimension manifold, the Caviar sphere. And indeed, this integer D makes a big difference. Right? It tells you whether it's exotic or not. So this shows the very subtle behavior of the groups that are involved, and the embeddings and the conjugate class on the embeddings is very important. Okay, so maybe this convinces you that these examples can be complicated. But let me first, before we go on, describe a picture which I will use throughout the rest of the talk, which holds for any cohomogeneity 1 manifold. So here is my picture of manifold where the quotient is M mod G. That's my interval. The quotient is one-dimensional. Here's a singular orbit, which I call G mod K plus. K plus is the isotropic group. Another singular orbit on the left, G mod K minus. And the principal orbit in the middle, which is bigger dimensional, so this is not a very good picture, is G mod H. Okay. This curve right here is a geodesic which is orthogonal to all the orbits. Goes from a point x minus to a point x plus, so minimal connection of the singular orbit simply. K minus is the isotropic group at this point. K plus is the isotropic group at this point. And it turns out H is the isotropic group at all the points of the geodesic in between. I have G mod K minus, G mod K plus, G mod H. How do they group together? Well, I look at the tubes around these orbits, or the singular orbits. So here I depict a tube around G mod K minus. Since the action is supposed to be cohomogeneity 1, these tubes must be invariant on the action at x-pi symmetries, but the principal orbit is supposed to be a hypersurface, must be codimension 1, so this tube must be a whole orbit. So here's one orbit, the center of the tube, and all the boundary of the distance tubes around it are the other orbits. They're the regular orbits. Same on the other picture here. Here's a singular orbit, the tubes around those must be regular orbits. Of course, in the middle they must fit together. This means that somehow the boundary of this tube and the boundary of this tube must be diffeomorphic because it must be G mod H for every point in between. Of course, these are now sphere bundles over the singular orbit, but one shouldn't think that the spheres have the same dimension. The total space of these sphere bundles just happen to be diffeomorphic manifolds, and I glue them together. Okay. Then I can, by using what's called the slice theorem, I can describe the manifold as a union of two halves. Here's a disk bundle. Here's a disk bundle. So I call it disk bundle around B minus, disk bundle around B plus, glued along this middle G mod H. Okay. These disk bundles have a very nice simple structure. They're what are called homogeneous vector bundles because, after all, the group G acts on this picture. Every point of the disk bundle is equivalent to a point in the slice around the point x minus. So I can describe it simply as the group G cross a slice. This is my slice at this point right here. That's simply a disk, divided by the isotropic group K plus or minus, depending on which half I look at, which after all must act on the slice because it fixes K x minus. So therefore I take the usual double quotient here, and this becomes what's called a homogeneous disk bundle. And that's what this disk bundle looks like. They're very simple disk bundles, homogeneous disk bundles. And the boundary of these bundles must be my G mod H, must be the sphere bundle, and they're diffeomorphic. So that's the picture I'm going to kind of have in the back of my mind throughout the talk. Now let's simply record this in a somewhat different fashion, which actually turns out to be very important. I should say that everything I'm doing on these slides, 2 slides here, is classical. It was done by Mostert in the 50s. This is when the topologists looked at these kind of spaces. And after that, except for this example by Zhang I showed you earlier, the topologists didn't pick it up again anymore because they just said, this is too trivial. This structure is so simple, what else can you do topologically? And I'll try to convince you that, in fact, there are lots of interesting topological questions one can ask of a kind of different nature than the topologists used to ask. But we'll see that as we go on. OK, here is my, I record this information now in a purely group picture. The group of the group and the isotropic groups. Gx on my manifold. K minus, K plus are the single isotropic groups on left and right. H is the principal in the middle. H must sit inside K minus and K plus as a subgroup, because after all, H fixes the geodesic, K plus and K minus fixes the endpoints. So these groups must be bigger. Okay. Then I record on the left-hand side the single orbit on the left, on the right-hand side the single orbit on the right. One more information, K minus mod H. What is that in our picture? Well, the group K minus acts on the slice, fixes the point X on the slice. Remember, the boundary of the tube is simply an orbit. That means that K minus must act transitively on the boundary of the slice. So it must act transitively on the sphere. And what's the isotropic group? Simply the group H, since it meets the slice right there, the boundary of the slice right there. So K minus mod H must be a sphere of that dimension on the left. K plus mod H must be a sphere of that dimension on the right. And these spheres can be different in general, these two spheres. So that's now a group picture. And what I claim is, and Mostert knew this already, and this is really quite amazing and wonderful, is that you can go backwards. Namely, take any group picture. This means a Lie group G, 2 subgroups K minus K plus, with a common subgroup H that belongs to both of them, with the only additional property that the quotient K minus mod H must be a sphere, and K plus mod H must be a sphere. When I have such groups, I can go back and construct the manifold out of it. I do it by essentially what I said over there. Now I'll write it down. On the left, I take the homogeneous disk bundle. K minus mod H is a sphere. That means K minus must act linear on the sphere, extends to the interior disk. That's my dl minus plus 1. And I can write down simply the corresponding homogeneous disk bundle. G cross the disk divided by K minus, which acts on the disk. On the right-hand side, I do the same thing. G cross the disk on the right-hand side, the extension of the action K plus to the disk of the bounding, whose boundary is SL plus. And then I take this homogeneous disk bundle. The middle must, after all, be the boundary of these disk bundles, which is G mod H in both cases by construction. So I glue along G mod H. That's my manifold. And now you just observe that how does G act on this kind of construction simply in the first coordinate, namely in G on the left. That's the action on each part here. And if you think about it, that's exactly the orbit structure that this is supposed to be. That is, the single orbits are K minus K plus, and the principal one is H. Therefore, I have constructed out of a group picture a manifold with each homogeneity 1 with a prescribed group structure. And this is really a powerful tool which hadn't been used previously, particularly not by topologists, for constructing new manifolds that are sometimes quite interesting. And I will mention some topological problems a little bit later about these manifolds, but I don't know the answer, which I think will be very interesting if I can answer them. Example, here is a group picture for the fourth sphere we discussed earlier. Remember, it was S3 acting as 4. The single orbits were RP2s. K minus was an O2, K plus was an O2, and H was a Z2 cos Z2. That's my group picture. This quotient is a circle. This quotient is a circle. So in this case, the single orbits are codimension 2. One thing also you have to be careful about is the following. This is sometimes misleading. Notice that the group K minus and K plus is almost the same. Particularly the conjugate in G, just a different embedding. Right? What happens if I change this group right here to look identical to this group right there? I'm allowed to do that. By my construction, it's again a quantity 1 manifold, because this quotient is a circle, this quotient is a circle. Is it the same manifold as a 4 sphere? The answer is no. It's a very different manifold. As an exercise, you can think about whether you can show that this is S2 cross S2 divided by Z2. So a small change in the groups can cause a drastic change in the topology of the manifold. And that's often quite interesting to do. let's look at this kind of group picture a little bit on other four manifolds. I did the four sphere right here. And now I can do the following. Just to tell you what things can happen, and I will also use it later on in my geometric examples. So I take my action of S03 and S4, this group picture right there, and simply lift it by the twofold cover from S3 to S03 into S3 to make it into an ineffective action, which will be easier to study, as we'll see. Then what are lifts of the O2s? They're simply a circle, union J times a circle. That's, as a group, is a pin 2. On the other side, it's a different circle, and I times that circle. The fact that different is the same as over there, that's important. And the lift of the diagonal mate is simply the quaternion group. And so this group picture also represents the four sphere in a different way. Now I can simply do the following. Remember I said that we can take any group picture with the only additional condition, the quotient of k plus and k minus mod h must be a circle. Let's take my S4 and take one component away right here. Let's take this component away right here. If I do that, since the quotient must be a circle, I must also take a component away right here. So I take the group generated by J here. Now, this is again a circle as before. That's a circle. It must be a four-dimensional manifold. The principal orbits are three-dimensional. What four-dimensional manifold is it? Okay. That's sometimes not so easy to recognize, but maybe a hint is that there is a simple map from this space to this space, and we just project along the orbits. From here to here, you have a two-fold cover. This is a two-sphere. That's an RP2. From this orbit to this orbit, I also get a two-fold cover. Right? This is S3 mod Z4, and this is S3 mod Q. Both are space forms. From here to here, it's not a two-fold cover anymore. It's one-to-one. This map is simply a two-fold branch cover from 4-manifold to S4. So what 4 manifolds do you know that admit a two-fold branch cover to a 4-sphere? So this should be a hint where maybe some of you might recognize what space is this. Any guesses? What 4 manifold admits a two-fold branch cover onto the 4-sphere? In fact, there was a recent paper by Attia and I forget the co-author. Yes? And Bernd. Attia and Bernd, where they generalized exactly this kind of two-fold branch cover to other high-dimensional examples. That's a very pretty example. No guesses, or otherwise you know it and you don't dare to speak up. The manifold is CP2. And CP2 indeed emits a two-fold branch cover onto S4. Very pretty two-fold branch cover. What's the branching locus? Well, the branching locus is this right here, which is one-to-one. Over here, that was my RP2, the very near surface. So here the branching locus is a very near surface. What is it here? Well, what's the action on CP2? It's very easy to describe. It's the action of simply SO3 on CP2, the linear action of SO3 on CP2. It preserves certainly the real points. The real points is an RP2. That's this RP2 right here. So branching locus on CP2 is simply the RP2. In S4, it's a very near surface. This orbit over here is an S2. What's the S2 in CP2? Well, what else could it be? It's a two-sphere. It must be the quadric. That's what it is. So here's a quadric. Here are the real points. And here's again a space form. That's my description of CP2 together with the two-fold branch cover. I can now iterate this procedure in constructing other 4 manifolds. By simply continuing to take two-fold branch covers. What can I do next? Well, I can take this picture over there of CP2 and take this component away right here. And it's still a circle. What happens then? Well, then I get a circle on the right, a circle on the left, and now I have to make the group Z4 smaller also, since the Z2 is plus or minus 1. Again, it's two-fold branch cover of a manifold onto CP2, and now the branching locus is the left-hand side single orbit, which are the real points in CP2, and the manifold you think about is simply S2 cos S2, on which SO3 acts diagonally. The diagonal action of rotations on S2 cos S2 that produce this group picture. And the singular orbit is simply the diagonal S2. So the branching locus here is the diagonal S2, and there it's the real points in CP2, two-fold branch cover. Well, I can continue once more. I can simply now take the Z2 away in the middle. Because then these quotients are still circles. Now the map from there to there is simply a twofold branch cover along both singular orbits. What manifold is it? The exercise is to show its CP2 connects some with minus CP2, which admits such a twofold branch cover onto S2 cos S2, which for algebraic geometry is well known. These are well-known maps, but they're depicted here right away in terms of group actions, which is very nice. Well, you can do one more thing. Why should I take either Z2 in the middle or 1 in the middle? I can take any cyclic group in the middle. Then this quotient is a circle, this quotient is a circle. It's a new comunidade 4 manifold. What manifold is it? And it turns out one can show, again, this is an exercise which is not too difficult, that this manifold is diffeomorphic either to CP2 plus minus CP2 and n is odd, like in this example right there, or to S2 cos S2 and n is even, like in the first example right there. So it repeats itself, but notice that since the group H changes, these are really different action. They're not linear anymore on CP2 plus minus CP2 or on S2 cos S2. They're very strange actions. They're nonlinear actions, which are very interesting to study. Infinitely nonlinear actions on comunidade actions on these two spaces. And of course, now I have an n-fold branch cover from this to this if I want to. And then I can show, and this was done a while ago by Parker, that if I look at simply connected compact form manifolds with a comunidade action on them, an example that's listed are all of them. These are the only form manifolds that emit such comunidade actions. So certainly among the set of all manifolds, a very small class, that shows that these manifolds are very special. But it also shows that if I generalize this to higher dimensions, one can do all kinds of things. One has a lot of freedom to play around, to construct other manifolds with different properties. And this is what I want to do next. So let's do a simple thing. Let me see which picture I want up. I think I actually want this picture up. Let me generalize the first picture on the left-hand side into a 7-dimensional manifold. Notice here it was S3, pin 2, quaternion group. Just do the following. G is S3 cos S3. Let's jack it up by 1, take a product. K minus, K plus will still be pin 2s, but now I have choices. I can embed the circle inside S3 cos S3 at a slope. The slope I denote by P minus, Q minus on the left, by P plus, Q plus on the right. Here are two pairs of integers which define the embedding of Q minus, Q plus into S3 cos S3. And H, I just choose a diagonal quaternion group again. And notice then this quotient is a circle, this quotient is a circle. If you think about it, actually, you should think about it a little bit more because that's not always true. That's what this condition right here is about. This is only a circle, namely the group H sits inside K minus K plus if and only if P plus and minus are congruent to 1 mod 4. Otherwise, this group picture is lying. The groups don't sit inside each other. If they do the quotient of circles, and I get the manifold, the principal orbit is 6-dimensional. The manifold therefore must be 7-dimensional. So it's a family of 7-dimensional manifolds that depends on 4 integers. So I denote them by m sub p minus q minus, p plus q plus. Okay. And then my next thing I want to do is study these 7 manifolds a little bit, both topology and also geometry of these 7 manifolds. It turns out they're very rich in structure, and I think they should be studied a lot more because I will pose several open questions. Here's some properties that Carsten Grove and I discovered over the last many years that we've studied this subject together. Each of these took a little while to realize, but they're not that difficult once you think about it. First, the manifold is 2-connected. Pi 1, pi 2 is 0, and pi 3 is a cyclic group that changes with the choice of the integers. So it's a 2-connected manifold. If I tell you what pi 3 is, that determines the whole cohomology ring by concrete duality. So topologically, I know exactly what the manifold is. And if one shows this to a topologist, they will say, oh, well, that's a 2-connected submanifold. Those have been studied a long time ago by us, named by C.T.C. Wall. He studied highly connected manifolds and classified them, they all claim, up to diffeomorphism. Well, it turns out these are not classified. I'll say a little bit about that a little bit later. So they're very interesting manifolds. They're highly connected, so they are very special. Next property is, for example, if I choose the integers to be 1, 1, 1, minus 3. So diagonal circle on the left and a circle with a slope on the right, I get the 7th sphere. With a certain linear action of S3 cos S3, it actually turns out the action is not effective. It's really an action of SO4. So it's a linear action of SO4 on the 7th sphere, which is also cohomogeneity 1. And this is actually the adult version of this action right here. This is a baby version, the SO3 action on S4. This is an action on S7, which is much tighter packed. The distance between single orbits is pi over 6. So it's doubly as densely packed as the 4th sphere, the 7th sphere, by these orbits. That means if I go along normal circle, I must hit these 12 times. Right? So I hit one single orbit 6 times, the other orbit 6 times. The picture looks like this, very densely packed, and here's my normal circle going back and forth before it closes up. So very interesting picture. And there are similar high-dimensional examples that are also interesting for spheres, but this is my favorite one. There's another one, an example that we discovered, namely if I just change in the third example, the left-hand side. The right-hand side is 1 minus 3 as for the 7th sphere. Left-hand side is minus 3, 1 instead of 1, 1. So one disk bundle is exactly the same. If you want, I take another copy of a disk bundle there, replace it with what I had before, and now group together. Very similar to a 7th sphere. What you get is a manifold with its well-known geometry. It's SO5 mod SO3, but not the usual embedding of SO3, the embedding of SO3 and SO5 that I get by looking at that action of SO3 and S4. That gives me a different embedding of SO3 into SO5. It's a maximal subgroup as opposed to the usual one. And that quotient is known in Riemannian geometry as the Berger space, because he discovered this is one of the few homogeneous spaces which admit a metric of positive curvature. So there are 2 examples in our family which have positive curvature, the 7th sphere and the Berger space. Another property that Carsten Gover discovered, which is a little more difficult, that if I choose the integers to be 1 and 1 in the first coordinate left and right, so 1p, 1q, this turns out to be an S3 principal bundle over S4. Well, if you think of two connected 7 manifolds, the first example that should come to your mind is an S3 bundle over S4 that also has pi 1, pi 2, 0, and pi 3 cyclic. So they have the same topology as an S3 bundle over S4. And here I'm claiming that at least the principal ones must be of this form. The order class of the bundle is then given by this formula, 1/8 p squared minus q squared. It's not hard to see that any order class can be achieved by choice of p and q. This means that every principal S3 bundle over S4 has a very strange cohomogeneity 1 action on it, a very large group acting on it. If you look at Milner's paper, where he looked at these manifolds to construct exotic spheres, that's where they first came up, and some papers after that, they construct also group actions. There's one by SO3, which is natural, and one by SO3, SO2, which is natural. So in 3 to 4 dimensional group acts naturally, but these are 6-dimensional group with a 1-dimensional orbit. And I have no idea what this looks like in terms of bundle structure. It just happens to be, one can show that these are diffeomorphic to a principal S3 bundle over S4. What the action looks like, I don't know. So one gets out of this also, if one turns this construction around, very interesting actions on well-known spaces. By first constructing the group picture, then I get a manifold, and now I ask myself, do I know this manifold? And if you're lucky, it's a well-known one, and here it is. And one gets very interesting group actions. So what are these actions good for? Let me now write down some properties that Carsten Gover and I also proved over the last 4 or 5 years. So we proved first the following theorem in 2000, a general theorem about cohomogeneity 1 manifolds, which shows that if I take a cohomogeneity 1 manifold with single orbit of codimension 2, so both the left and right have codimension 2 orbits, it must have an invariant metric of non-negative curvature, non-negative sectional curvature. And these are very interesting examples. There aren't that many examples known in Riemannian geometry of non-negative curvature, and any new class should be very interesting to see what these manifolds look like and study their properties. As a corollary then, by looking at case D, we see that, that all of these manifolds, since the codimension of the single orbit is 2 on both left and right, must carry a metric of non-negative curvature. So they all have interesting geometric structures. In fact, that's how we ran across them. In particular, S3 principal bundles S4 have non-negative curvature. And you can also jack this up to get lots of exotic spheres non-negative curvature. but that's not what I want to talk about. Here are now the problems I'd like to mention that I think should be studied for these manifolds, for this general class of manifolds. The first problem, an obvious one, is classify these manifolds up to homomorphism and diffeomorphism. That's my problem 1 here. If you look at the CTC wall papers of classification of high-connected manifolds, he does this up to connected sum with exotic spheres only. And even then, it's very difficult to apply his papers because you have to compute certain invariants that are very difficult to compute. So it's unknown how to do this in general. On the other hand, if one looks at the Eels-Kuiper papers, which came right after Milner's paper on exotic spheres, one has to compute just a single invariant, the Eels-Kuiper invariant. But it's not known how to compute this. And it turns out to be very difficult. Then if one does this, one would then compare this with the classification of homomorphism, the homomorphism and diffeomorphism of S3 bundles over S4. Because after all, we already saw here that there's some of these are the same, but here I take only principal ones, because there are many S3 bundles which aren't principal. So in other words, which S3 bundles over S4 carry comunity 1 actions? That I think is a very interesting question. What one knows about this, I'll talk about in a minute. So here, that's my third question here. How many S3 bundles over S4 carry comunity 1 action? All principal ones do, but one also can show the ones with Euler cluster plus or minus 1, which contains the exotic spheres of Milner, do not. So these exotic spheres do not carry comunity 1 action. But I bet that many of the other S3 bundles do. The answer won't be simple. It will be a little more complicated. And of course, an important geometric problem, the fourth problem here, study the existence of further geometric structures on these manifolds. They're very interesting manifolds. We know some already. What can you say about the geometry of these manifolds, besides non-negative curvature already, which we did in the previous theorem? For example, do they carry Einstein metrics? Do they carry Einstein-Weil metrics? Or do they carry metrics of positive curvature, like on the 7th sphere in the Berger space? And many other structures that you'd like to study, you can see if they have such structures on these manifolds here. And typically, because the action is by comunity 1, means the problem is reduced, typically say from, if your problem is a PDE, the problem becomes an ODE, which you can try to solve. And I want to talk about that a little bit later. Some remarks. The results should be very interesting, and I want to compare it, for example, with the classification that has been done maybe 10 years ago by Kreck and Stolz. They classified these Alaf-Wolof spaces up to homomorphism and diffeomorphism. Very interesting results. And this is a much bigger class, and I think also there will be very interesting results if one does this. It's known the following 2 cases only. That's the only results I know about it. The first one is the principal bundles I mentioned already. The second one is a more recent paper by Götte, Shankar, and Kitschlu, I think in 2002, maybe 2003. They showed that M1 minus 3 minus 3, 1, that's our Berger space, remember, is actually diffeomorphic to an S3 bundle over S4. And this is actually very interesting and very surprising because it shows that this Berger space, which is a space of positive curvature, which, by the way, was one of the few examples of the known manifold of positive curvature which did not emit a bundle structure, or weren't known to emit a bundle structure, because the group SO3 is max and SO5. There's no natural way to construct a bundle structure out of this. Never it has one. It must be diffeomorphic to a certain S3 bundle over S4. No one has any idea what the diffeomorphism looks like. If you could construct this diffeomorphism for me explicitly, I'll take you out at any restaurant in Rio of your choice. I predict that this is impossible. In any reasonable form, I want an explicit form in some sense I can look at, right? And that I think is impossible. So these are done by a surgery theory. Actually, what they did, it's a very long paper, very difficult paper. They computed this Eels-Kuiper invariant analytically by looking at heat invariants and computing the heat invariants on this homogeneous space in long, long computations. And eventually, they compute the Eels-Kuiper invariant for this particular space only and show it's the same as the 3 bundle S4. Very interesting result. Okay. Now I have 50 minutes left, and maybe I will let the audience make a choice, because I will now talk about some applications in geometry. So this is like the next topic. What can you do with these spaces? Well, you can study their geometric properties, say of general comunity 1 manifolds, and I could do one or two things. Let me put the slides on here. Here's a very interesting metric by Hitchen in 4 dimensions, comunity 1 metric, that he constructed almost 10 years ago. It's absolutely amazing. He's studying this paper more and more. and it's really a gorgeous paper. And these metrics, certainly, they're studied by physicists, but not that much by geometers. They have to be studied further. And I'm in the process of doing that. Here is another picture. That's a picture of an infinite sequence of comunidade metrics, comunidade Einstein metrics on the 5-sphere, which were constructed by Christoph Böhm a while ago. So here are comunidade metrics on S5, and here are comunidade metrics on, actually, the manifold, the underlying manifold is S4, but the metric is an orbifold metric. So I can either explain these formulas, they look horrible, but they're actually beautiful, or can explain these pictures. It's the choice of the audience. These are Einstein metrics, and these are self-dual Einstein metrics in dimension 4. Any preference? Probably have time for only one topic. No preference? Are you sure? Yes? This one. Okay, that's my favorite one also. Very good. Thank you, Harold. To explain these formulas, I have to remind you of a few facts. And I didn't have to time to prepare these slides, so I put on the blackboard. Facts about self-dual Einstein manifolds. These are 4-dimensional manifold. So the metric is Einstein, that's clear. Where to do that? Some light for the blackboard? Some light? Thank you. So these are first and 4-dimensional manifolds. They're Einstein, they're self-dual, or depending on the orientation, you choose anti-self-dual. That's a matter of choice of orientation. And this simply means that either the plus part or the Weil curvature tensor is 0, or the minus part of the Weil curvature is 0. And that depends on orientation. So half of the Weil curvature is 0, so half conformally flat was another name that was frequently used for these metrics. They've been studied quite a bit, even without the Einstein condition. So simply this self-duality condition here implies that there exists a twistor space. So a 6-dimensional manifold which fibers over the 4-dimensional manifold with fiber S2. And it's very easy to describe. The inverse image of a point on the 4 manifold is simply the complex structures on the tangent space of the point P in M4. 4-dimensional vector space, you look at complex structures on this, which preserves the orientation, and that's a 2-sphere verse in dimension 4, so it becomes an S2 bundle over M4. Very easy to construct a complex structure on this by just putting together the one on the base and on the fiber, which is given naturally. And then this result is that N6 is a complex manifold if and only if W plus or W minus 0. Okay, so the complex structure that you define as manifold naturally must be integrable if and only if the metric is half conformally flat. So this then introduced the whole industry. This is called the twistor space of the manifold. Now you can use complex geometry to study the twistor space. Particularly one also knows that if in addition the metric is Einstein, that implies that my 6-dimensional manifold is K Einstein. So now complex geometry enters the subject, and you can study these threefolds, complex threefolds, to say something about the 4-dimensional manifolds themselves. And here are some typical results. First, Hitchen proved a long time ago a result which at first sight looks disappointing, but actually quite interesting. He showed that if I have such a 4-dimensional manifold, self-dual Einstein, and the Einstein constant of the Ricci tensor is positive, the positive Ricci tensor, this implies that there are only 2 examples. M4 must be CP2 or S4. This is standard metric, round symmetric on S4 and the Frobenius 2D metric on CP2. No other examples with positive scalar curvature. There are many interesting examples with negative and 0 scalar curvature. That's a different story. I'm only talking about the positive scalar curvature case right now. This was proved by Hitchen a long time ago. And this seems to say that this case is less interesting because you have only 2 examples. But actually, later, there was a paper where Galetsky and Lawson discovered that they are self-dual Einstein orbifolds. And many of them. If I don't require my space as a manifold, if I allow an orbifold structure, there are many examples. In their cases, they had weighted CP2s. So CP2 with certain orbifold singularities, 3 points with orbifold singularities. And since then, many other orbifold examples were constructed. That's a very rich class of manifolds, and it's very interesting to study them. Has been done also a lot by physicists. This seems to have lots of important applications in physics, which I'll only briefly mention. So maybe I'll mention one application that physicists are particularly interested in, which is a result by Robert Bryant and Solomon, they proved a while ago, which says that if M4 is self-dual Einstein, then out of such a metric you construct a metric in dimension 7, which is holonomy G2. So there exists a 7-dimensional manifold with a Riemannian with holonomy G2. In the sense of Riemannian holonomic group in the parallel translation. And in fact, the space is very simple. You just take the space of self-dual or anti-self-dual 1 forms on your 4 manifold. So the same one where the bulk cotangent vanishes. That's a 3-dimensional vector bundle of your 4 manifold. So it's 7-dimensional. And on this, you can very easily put a metric. The metric is temptingly simple. 1 plus r to the minus 1/2 times the metric on S3 plus 1 plus r to the plus 1/2 times the metric on M4 pulled back to the vector bundle. In some sense, you just put together the metric on the 4-dimensional manifold. You think of it, you put it on the horizontal distribution of the natural connection in this vector bundle. That defines a metric upstairs multiplied with a radial function, r the radius in the fiber to the origin. And add to that the following metric on the fiber, the usual metric or the Raunsian metric multiplied with a certain function in terms of radial coordinate to the origin of the fiber. And this is then has holonomy G2. So whenever you take an Einstein as help to an Einstein manifold, this metric is holonomy G2. And they also had many other examples in this paper. Of course, this one seems to be the most disappointing application, because it says that the only ones you get is for S4 and CP2. And for S4, you get simply the Hopf bundle with holonomy G2. That's a well-known example. For CP2, you get what? So for S4, it's Hopf. For CP2, you get one where the sphere bundle of the vector bundle, that's a 6-dimensional manifold, must be SU3 divided by the center of SU3. So a certain 7-dimensional manifold. This is a Wall space of positive curvature, well known. So if I take this as my sphere bundle, look at the corresponding vector bundle, it's holonomy G2. Okay. These are 2 very nice examples, but somewhat disappointing since one gets only 2 of them. And actually, these weren't known before the Bryan-Solomon paper, so there were no new examples, but they were isolated. Well, but now look at this situation over here, that you also have lots of self-dual Einstein orbifolds. Do the same construction. The construction is completely local. And you get, again, a metric with holonomy G2, which now must be an orbifold metric because your metric on the base has an orbifold singularity, so your metric on this total space also has an orbifold singularity. So you get metrics holonomy G2 which have orbifold singularities. And actually, the physicists are very interested in those. They want metrics which aren't smooth. So one thing I've been told, because this changes every few years, Calabi-Yau is out, holonomy G2 is in. And holonomy G2 is here to stay. Calabi-Yau is not really what they wanted. They really want holonomy G2. And they want holonomy G2 with singularities. That's what they really are interested in. For example, orbifold singularities are even worse. For example, also on a non-compact space like this, these are non-compact here, you want to look at the behavior of infinity. Is the metric complete? And what's the limiting structure at infinity? Because this will be a typical behavior of a really bad singularity near the point of the singularity. That's what these metrics will look like, kind of. They're very interested in these non-example and the behavior at infinity. Here, I'm not saying that this metric is complete. That's not known in this generality. Where if I take any orbifold metric, which is helpful to Einstein, look at this holonomy G2 metric, is it complete? That's not known. But the physicists have written dozens of papers in the last 2 years. They look at special cases. They write on very special solutions, and then they examine completeness, and they look at the behavior of infinity of these metrics, And they want lots of examples of these as examples of singularities for metric G2 renome. They don't want smooth examples, they want singular ones for some reason. I have no idea why, I couldn't understand it. Okay, so that's the background somehow. Well, some other examples. That's where Hitchin came in again a few years ago, and that's what I want to explain now in the last 3 minutes. Actually, maybe I can put the formulas up there, since that's what I want to explain. And I can't do this justice since I have only 3 minutes left, but let me try. So Hitchin said the following. Let's look at a very simple situation where you don't try to find all possible self-glued Einstein orbifolds. This seems to be way too complicated. Classification is out of reach right now. Let's look at examples which are common to D1. So he took a 4-dimensional manifold, and we saw lots of them already earlier. And remember, they all had an action by S3 on it. Right? All the examples had an action by S3. So Hitchin considered an action of S3 on this 4-dimensional manifold where the principal orbits are 3-dimensional, so a quotient of S3 possibly. Okay? And the examples we discussed earlier. And then he said, can you find invariant metric on the space which is self-glued Einstein? Of course, self-glued Einstein now becomes simply, if you think about this metric, what does this metric look like? Well, I have these principal orbits. They're all quotients of S3. Manifold looks like metrically a product of an interval across S3 mod a finite group. And metric is like dt squared plus a family of metrics gt, which are simply homogeneous metrics on this space form. So manifold is simply described by a family of homogeneous metrics on the space form. These here you can decide if you want to by the metric on the Lie algebra. And the first thing Hitchin showed was that, well, if it's self-glued Einstein, this metric is fairly simple. In principle, this could be any left invariant metric S3, a 3 by 3 symmetric matrix. That sounds pretty bad. He showed it must be diagonal. So gt is f1 squared d theta 1 squared plus f2 squared d theta 2 squared plus f3 squared d theta 3 squared, where d theta 1, d theta 2, d theta 3 are the usual based on S3. So 3 functions, depending, of course, on your parameter. So the parameter of your normal gestic, if you want to, describe this metric completely. And now it's obvious that the self-glued Einstein condition must become an ordered differential equation in terms of these 3 functions. Question, what does it look like? How complicated is it, and can you solve it? And it's a doozy. Here's a differential equation. Let me try to say how to look at this, because this takes a while. So here's my metric. D theta 1, D theta 2, D theta 3 are my 1 forms on S3. The coefficient in front of us are supposed to be the 3 functions at 1 and 2 S3. And it turns out to be important to allow yourself a little bit more freedom. Instead of looking at dt squared, which is the arc length parameter, you take a function times the arc length. So here's my x, new x parameter. G is a function of x, f1, f2, and f3 are functions of x. So you have to describe these 3 functions of x somehow for the metric to be self-glued Einstein. So do the following. Here's f1, f2, f3. Looks like they're functions of what? X, y, and z. I want to make them into a function of x only. So I define z as a function of x and y prime. So I'm still not done. I must get a function of x only. So y must be a function of x also. Or before I do that, this conformal factor g, it's common to all of them here, is this function in terms of x and y also, and z. Okay. What's left? What is y? For this to work, y must be a function of x. Once I know y, I plug it in here to get z as a function of x. I plug both in here to get g as a function of x. I plug everything in here to get f1, f2, f3 as a function of x. The question is, what is now the differential equation on the function y as a function of x? Here it is. Second order equation. That's actually a very well-known equation in analysis. It's called the Pony-Leff equation of type 9. It certainly depends on various constants. These constants here are 1/8, 1/8, 1/8, and 3/8. So it's a very special Pony-Leff equation. These has been studied for probably 200 years at least, with various special solutions and various ways of rewriting them and studying them. They're extremely difficult. And in special cases, they can sometimes write down explicit solutions that are very complicated in terms of special functions. Okay. This hasn't been done here, so certainly the physicists looked at these also and they couldn't solve it. And what Hitchin observed was that, well, let's lose the complex geometry. let's use our twistor space. Okay? There's a 6-dimensional manifold, and in this twistor space you can do algebraic geometry, and you can try to describe the metric on your 4-dimensional manifold in terms of a certain object in terms of your 6-dimensional Kähler-Einstein space, supposed Kähler-Einstein space. If you do some complex geometry up there, you have to solve certain geometric problems, algebraic geometric problems up there, and eventually Hitchin comes up with an absolutely amazing answer to the problem. He writes down a solution y of x which is essentially explicit. Now he says this in his introduction, this metric is explicit, and the more you read the paper, you have to understand what some people mean by explicit is not necessarily what others mean by explicit. Here is an example of what he means by explicit. Can I get the lights here again? Okay. Here are 4 examples, the simplest ones that Hitchin found. First example is an interesting description of the down symmetric on S4, which after all is self-true Einstein. Right? Why is this rational function of R, and x is another rational function of R? If I substitute, I get y as a function of x. Lo and behold, this satisfies the Palestra equation, and therefore gives you via this long process a complicated metric which describes the down symmetric. And this is actually not that bad. I didn't have time to produce some transparency with these formulas for the metric. They get quickly extremely complicated. Second example is the usual metric on CP2. That's also self-true Einstein. Well, that's given by a very simple formula. Y is equal to R, x equal to R squared. So y is equal to square root out of x. So it's algebraic but not rational. Next one is a metric on S4, which is now an orbifold of the type that, of the following type, along one singular orbit. Remember, it has an action of S3 on S4, which was S3 on S4, which had singular orbits RP2 and RP2, the very nice embeddings. This metric here is smooth along one RP2, because in between is completely smooth. Along the other RP2, it's simply an orbifold singularity where the angle normal to the Veronese surface has angle pi over 2. Pi over 2, yes. So that's not smooth, but a real orbifold. And here's the formula. Y is this rational function of R, x is this rational function of R, y becomes function of x, satisfies Palestra, and now the formula for the metric becomes pretty bad. I would need a whole transparency to write it down. And he found another one, which is explicit and rational, where the normal angle is again smooth along one RP2, single along the other 2 with angle 2 pi over 3. Here's a function y of R, and here's a function x of R. And this again solves Palestra and becomes a metric which looks pretty horrible. Probably wouldn't fit on one slide. What Hitchin shows in this paper, it's actually quite amazing. It's a paper that appeared in JDG, I think in 95 or so, is he shows that for every integer n, there exists a solution of this Palestra equation, which you can write down explicit in the sense that it's an algebraic solution, which for each integer, if you worked at it, you could write it down explicitly if you wanted to. Okay. In these examples are some simple cases where it's actually very, very simple, where the algebraic functions become rational. Okay. So for every integer n, he gets such a metric with a property that along one RP2 it's smooth, along the other RP2 it has an angle 2 pi over n. Exactly one for each integer n. These are all orbifold metrics which are self-true Einstein and induce therefore an orbifold G2 metric in dimension 7, which the physicists have written many papers about, because they're very interested in geometric properties of the orbifold metrics. And it's actually quite difficult to show, and that's what Hitchin does in his paper and requires a lot of work, is that these metrics exist exactly one for each integer n, and that the solutions are really algebraic. They are algebraic solutions. If you want, you can write them all down. They become horribly complicated, but he has a recipe for writing down any one of them. I once wrote down one for the angle pi over 2 pi over 3, 2 pi over 3. That's algebraic and not rational, and it's pretty bad. It requires 3 slides to write down. But you can then use these to study the metrics geometrically. You can draw nice pictures of them, and unfortunately I've done this in Maple, and I didn't bring them along. The functions are very beautiful, and you can study them geometrically, like study the curvature properties. I'd like to know a lot more about these metrics, what the curvature properties are. And I started doing that, and it looks quite interesting. Furthermore, he shows all the following, which is, for him wasn't interesting, but I think is interesting geometry. He shows that, that not only is there such a metric for each into the n, even for each real number alpha, bigger or equal to 1, there is a solution of this Pan-Lev equation, and therefore self-ruled Einstein metric, which is smooth along one RP2, along the other RP2 has the angle 2 pi over alpha. So it's not an orbifold anymore, but still it's unique. So actually it's a one-parameter family of self-ruled Einstein metrics, which go through these orbitfolds into the values, otherwise become what are called Alexandrov spaces. Because as long it shortens the normal angle of the RP2, and therefore becomes an Alexandrov space with a lower curvature bound. It's actually very interesting Alexandrov examples. And what has to happen, for example, is that you start with alpha equal to 1 is S4. You go through one parameter family of metrics to CP2. It's a smooth family. It must have positive section curvature, I'm sure. It continues through CP2 to more families, which has to remain still to have positive curvature. At some point it ends. I'm not quite sure yet where. I'd like to find out. It continues through all these order examples. In between, you have Alexandrov spaces. And they're unique. There's a unique family like this depending on one single parameter. It's an absolutely beautiful paper, and I think the geometrists have to study these examples more and determine their properties. And they induce metrics in dimension 7 that follow from them. It's a wonderful paper, and it also, again, comunidade 1 manifolds in geometry of comunidade manifolds. And many other examples, like the pictures I drew here, are very nice Einstein metrics S5, which are also very difficult to find. This paper, Christoph Böhm, is also very beautiful. So there are many problems one can ask, which are very difficult to study. The order differential equations can be very complicated. Or if you study curvature problems, then you don't have ODEs, you have differential inequalities, which are very complicated. So I think it's a beautiful subject with many open questions, and I hope I'm getting some of you interested here to think about some of these, because there's a lot to do, and it's very interesting. Thank you very much.